All right, super fast recap. Up to this point, we've looked at graphical, numerical, and analytical approaches to evaluating limits. And under this category of analytical approaches, we have canceled out removable discontinuities to simplify things algebraically. So if we just call that the cancel technique, we've looked at examples kind of like this and more complicated versions of this, where we've got a common term that we can cancel out, and then we are left with a simpler problem in which we can use direct substitution. This conjugate technique has resolved the square root issue. We've multiplied a situation like this on the top and the bottom by the conjugate, which means the same thing as a numerator, only with the opposite sign. And what that does is it effectively eliminates our discontinuity in the denominator. Recall that this fraction equals 1, so we're not actually changing the problem. And when we multiply this through, when we use our FOIL acronym here and here, we are left with this. And actually, just kidding, I didn't FOIL the denominator, because when I FOILed out the numerator, I saw that I got x minus 4, which is great, because I have an x minus 4 in the denominator. So just like number 1 with the canceling technique, this actually is an extension of the canceling technique. We're still canceling out a term, but we're allowing ourselves to do that by multiplying by the conjugate. So in this example, when we plug 4 in now, we've resolved our problem on the denominator, and we get 1 over the square root of 4 plus 2, which is equal to 1/4. Alright, so the point that I want to make here is that both of these techniques allow us to deal with a removable discontinuity. Algebraically, we are removing our problem spot on both of these examples and all the examples that we've looked at most recently. We can remove our discontinuity, meaning that we have a removable discontinuity, and graphically what a removable discontinuity shows up as is a gap. A removable discontinuity is a gap or a hole, unlike a non-removable discontinuity, which manifests itself graphically as an asymptote. So let's jot this down. There are two types of discontinuities that we're looking at right now. There are more, but for now there are removable and there are non-removable discontinuities. Graphically, a removable discontinuity gives us a gap or a hole, and graphically a non-removable discontinuity shows up as an asymptote. With a removable discontinuity, a term or terms will cancel out or be removed so that the denominator no longer is equal to 0. With a non-removable discontinuity, the terms can't cancel out. They don't cancel. So with the rest of our time, I want to look at an example or two of this scenario where we have a non-removable discontinuity and nothing cancels out. So here's our example as the limit as x approaches 2 of the function x squared minus x plus 5 over x minus 2. If we approach this like we do all the other ones and we try to just plug 2 in, this will become 2 squared minus 2 plus 5 all over 2 minus 2, which will become 4 minus 2 plus 5 over 0, which is 7 over 0. Now, before you just say that this doesn't exist, it could be that the answer is that it doesn't exist, but we don't actually know that. But this is a little bit confusing because 7 divided by 0 is actually not indeterminate form. 0 divided by 0 is indeterminate form, as is infinity over infinity. That's indeterminate. You can't determine what that answer is. As also is infinity times 0. You don't know if the answer is infinity or 0 or doesn't exist or what's going on. And another indeterminate form is infinity minus infinity. You should jot these down if you haven't. these are indeterminate forms, but 7 divided by 0 is not indeterminate form. Now again, as you look at this example, you are probably tempted to say that the answer just doesn't exist because 7 divided by 0 doesn't exist. And it actually is true in this example that the answer is that it doesn't exist. But we need to pursue this thing a little bit further because it could be in a similar sort of situation that the answer could actually be infinity or negative infinity. Actually, in this case, it would just be positive infinity. But we need to search this out and see what's going on. So let's go back up here. Let's start at the beginning again and try to algebraically modify this thing to get somewhere. And sadly, there's not really much that I can do algebraically to change this. I can't factor the top. I can't factor that numerator. So we're kind of left in a lurch. I have a non-removable discontinuity when x is equal to 2. I cannot algebraically remove it or cancel it out. Therefore, it is non-removable. So I want you to remember that a non-removable discontinuity graphically shows up as an asymptote. So what this means, without knowing really what the graph looks like, what I do know is that I have a vertical asymptote at positive 2. And what a vertical asymptote, remember, is doing is it is a point or a line. It's a line that our graph is getting infinitely close to. So it could be that our graph looks something like this, in which case the answer to this limit problem would be positive infinity. Or it could be that our graph looks something more like this, in which case the answer would be that the limit doesn't exist because the limit from the left doesn't equal the limit from the right. So at this point, to actually figure out what the limit is, we are left with two options. If we can graph it. We could use a graphing calculator, or if we don't have a graphing calculator, we could plot some points. Or we could do a numerical approach where we make a table of values and look at what is happening here. We've looked at both of these approaches already, and in either one of these would shed some light on what's going on. So to sum this up, algebraically, if we can't do anything, we are left to resort to the previous two options to determine what's going on in this situation where we have a non-removable discontinuity. So let me resolve this for you both ways. Graphically, this is what the graph actually looks like. And numerically, I'm just going to do a super simple analysis over here. I've plugged in, I've got a table of values, and I've plugged in 2, at which point the function doesn't exist because I'm dividing by 0. And then if I go just a little bit to the right, just 1/10 to the right and 1/10 to the left, that will shed some light on the situation. If you plug 2.1 in for x into this function, your output value is going to be 73.1. Oops, 73.1. And if you plug in 1.9 for x, you end up with negative 67.1. So knowing what we know about a vertical asymptote, and knowing that as we approach from the left, we're getting a big negative number, and as we approach from the right, we're getting a big positive number, we can we can with all certainty say that the limit from the left does not equal the limit from the right, and therefore this limit fails to exist. So the answer here is that the limit does not exist. And we've looked at evidence of that both graphically and numerically, because algebraically we were stuck. We could not cancel anything out. We had no removable discontinuities, and so we approached it these two ways.